A very good morning, everyone. Welcome to day 3 of ASCAT. Over the past 2 days, we have had enlightening discussions, thought provoking research presentations, and engaging interactions. As we step into the final day, we are excited to continue this journey of knowledge sharing. We begin today's session with an invited talk. The session chair for the morning session is Professor Supratim Biswas. I request you to kindly chair the session.
Go there or speak from anywhere? Okay, it's my great pleasure to invite my younger colleague from IIT Bombay, Professor Supratik Chakraborty, whom I know him for a very long time. He needs no introduction to most of us, but still, since I have been asked to do so, I'll give a very brief thing. So he's from IIT Kharagpur, BTech Computer Science and Engineering, and then he did his PhD from Stanford in electrical engineering. So there's a very good combination. I've not met too many people who have switched from CSE all the way to E. Very accomplished academician, has been the President's Gold Medal awardist of IIT Kharagpur. But much more than that, he's a very, very nice person. And his coverage from theory to systems is amazing. I know him from his almost first day when he came to give his faculty talk at IIT Bombay in the evening. And after his talk, he said, "Why don't you apply?" So he then downloaded from Stanford his resume and gave it to us. That's the way the whole thing began, the journey. So he has been a very prized addition over there. He's an excellent teacher. You can take it from me. I'm sure you will get evidence of that today itself. But a very nice human being. He has addressed concerns of students at the highest level. And you know that IIT Bombay gets the top 50 or whatever, all India ranked people. We also have some people who struggle. So we used to run a program together called Academic Rehabilitation Program, where we used to look for the weak students who are academically weak for some reason. And he has taken a great amount of interest in that. So he has many claims to fame. You can read his website. But one thing is interesting to mention, we're discussing this morning. So while he was doing his PhD at Stanford, his roommate later on became a very illustrious people. At that point in time, he was another colleague who happens to be Sundar Pichai of Google fame. And Supratik has some very interesting stories about him. But that apart, I think we are all eagerly waiting to hear him out. So thank you, Supratik, firstly for accepting our invitation, coming here, and spending the day, 2 days with us. Thanks.
Thank you. Okay, thank you, Supratim, for the very kind introduction. And thank you, everybody, for showing up here on a Saturday morning. Today is also March 8th, International Women's Day. So wishing everybody a very happy International Women's Day. Thanks to Supriti and all the organizers for inviting me here, having me over here. Unfortunately, I could not be present over the last 2 days because of commitments at IIT Bombay, but I'm looking forward to all the sessions today. So perhaps unlike the invited talks over the last 2 days, this talk is not going to have too much of a connection with cellular automata, but I have still found some connections, and I'm going to talk about that in a slide. Hopefully that will be of interest. But I was told that it is okay to talk about some of the work that we are doing, and maybe there are connections that I have not yet explored, which all of you are experts here in cellular automata. I'll be happy to talk about that. So what I'm going to talk about today is some recent results we have on this problem called Boolean functional synthesis. I'll explain what this problem is. So let me start off with acknowledgements to, this is not work done by me alone. So several collaborators, a lot of students, colleagues, and also many fruitful discussions with people elsewhere. not necessarily from IIT Bombay. So, I'm speaking on behalf of all of them. Okay, so here is a cartoon where, I would like to say that for a lot of computer engineers out there in the industry, their typical day at work is something like this. Somebody tells them that you need to design a program or a circuit or maybe a cellular automaton which needs to do some task. Okay, there is a task description, and then you have to write a program or design a circuit to do that. And so this task description, in my case, I will just represent by a box here, which takes some inputs x1 and x2 and produces some output y. And the computer engineer's task is to build this system, starting from some description of what the system should do. But typically, this description doesn't clearly tell us how to design y as a function of x. So I'll give you some examples. So typically, a specification can be in this form, that I can provide a table saying that when x1 is 20, x2 is 3, y should be 20, and so on. I can list out a few cases. So this is also called specification by examples. I could write a specification as a logical relation where I'm saying what is the relation between y and x. So for example, here there are several inequalities between y and x. So I want the system to be such that whenever I give x1 and x2 as inputs, it generates y such that this relation is satisfied. Note that this is not exactly telling me what should y be as a function of x, but it's just telling me what is the desired property between y and x. Or, in these days of large language models, we can also give a specification in a natural language, and maybe, we can try to convert it from the natural language to, more formal specifications like that. And then our goal is, given maybe the specification in one of these formats or maybe more than one of these formats, we have to come up with this system. So this is, at a certain high level, this is the job of most computer engineers. They're trying to design something such that it satisfies some specification. So what does the engineer do? So after some thinking and scratching of head, and let us say in this case, the engineer started off from this logical relation, just telling what the inputs and outputs should be, how they should be related to each other, without specifying how exactly the output should be generated from the input. And so maybe after scratching head for some time, the engineer comes up with this program, says that, yeah, I found this program, and I think this does what the specification requires me to do. So well and good, but then a colleague comes and says that, well, how do you know that what you've designed is really satisfying the specification? And more importantly, there is nothing very sacrosanct about the specification. What if I change this specification? Will you again be able to scratch your head and come up with another program like this, right? So this becomes a problem because out there in real life, specifications are sometimes fluid. They keep changing. Somebody writes something, figures out a problem, then changes it, again writes something, changes it, and so on. So over time, specifications do mutate. So we would like to be able to, design, this guy has to design this program for perhaps changing specifications, and more importantly, has to somehow ensure that whatever the design is, it's actually correct. It's provably correct. Okay. So, so the computer engineer thinks that, well, if instead of having to scratch my head and write this program every time, it would be really nice if I had an algorithm which could do this, right? So what this engineer wants is something like this, that you can give your specification in whatever format you want. And then maybe there is an algorithm, which we will call the synthesis algorithm, which magically outputs the system along with a proof of correctness of the system. Okay. So we can start off with the specification, and any one of these specifications doesn't have to be all of them. So maybe we start off with this, and then it goes inside the algorithm, and then the algorithm automatically generates this program or circuit or cellular automaton, which provably satisfies this property. Okay. And now this is good because now if you want to go and change the specification, so maybe I have introduce some changes in red. I don't need to scratch my head again. I just feed it to the same algorithm, and out comes another system along with a proof that that system satisfies the new specification. So this would be really good. And in the literature, in fact, so this is what is called automated synthesis or automated program synthesis. And in the literature, this has been called one of the holy grails of computer science. If we could directly generate programs, I mean, just think about it, right? I mean, of course, we are very, very, very far away from achieving this goal, right? If I can say that I can generate a compiler just by writing the specifications of the compiler, and it would be provably correct. I mean, we are nowhere close to that, but this is kind of like a blue sky problem that we want to have in front of us and say, how far can we advance towards that? So in this talk, I'm going to focus on this problem, the synthesis problem, starting from logical relations and trying to generate provably correct systems. Okay, so we will focus on what these kinds of algorithms can be, what are the issues involved, how hard is the problem, what can one do, and as I promised, I have one slide on cellular automata, try to bring some connections. Okay, all right. So is it clear what am I going to talk about? What do I mean by the synthesis problem? You started from some specification which does not tell you how the output should depend on the input as a function. For example, this does not tell me what y is a function of x1 and x2. It just tells me what is the desired relation between x, and there could be many systems which satisfy this. We just want one of them, but along with that we also want a proof that what we have designed is correct. Okay. Great. So at a generic level, what we are talking about is that we have a formula which relates some inputs and some outputs, just like those inequalities we had. Yes. No, the relation is given. I'm going to find out the function. That's a special case of this. If there is no input and no output, then it is not clear what that system is doing.
That should be defined by the engineer only. That what would be the probable outputs and what would be the probable.
Right.
Can we start it from here?
Yeah, so you are going one level before about who writes the specification. So I'm not talking about who writes the specification. I'm saying somebody has written the specification. Now I'm trying to generate a system out of it, right? So just to give you an example, and I'm going to refer to this example. I want to factorize an integer. Okay, so it's clear what I want to do. Everybody understands. I'll give you one integer. You have to give me two integers whose product is this. I'm not telling you how to do the factorization, right? So the specification is clear that the inputs and the output should be related by product of the output should be equal to the inputs. But I have not told you how to do factorization. In fact, this is still an open problem about how to do efficient factorization. We know how to do factorization in a not very efficient way, right? On the other hand, if I told you the same problem the other way around, that I'll give you two inputs and you have to give me an output whose factors are the two inputs, then it becomes a very simple problem. You just multiply these two numbers and give the output, right? But if I just flip the roles of what are the inputs and the outputs, suddenly it becomes a very hard problem. So having a specification and having the system are two different things. A specification is often easier to state. It's my wish list. Once somebody has decided what are the inputs and what are the outputs, right? If one has to decide what are the inputs and what are the outputs themselves, that goes at an even earlier level of the entire design flow. Right? For a compiler, my input should be a source program, the output is a maybe assembly program, and the desired property is that their semantics are identical. This is very easy to state, but to write the compiler is extremely difficult. Right? Okay, so so I have the specification as a formula between inputs and outputs, and I have to design this system over here, right? With some guarantees that this is actually correct. So what we are talking about is that can we algorithmically generate the y's as functions of x's such that in this formula, when I substitute f of x instead of y, the formula is satisfied for all possible x's, right? And we will see that sometimes this for all possible x's becomes a little problematic. So we will say that whenever it is possible to satisfy, maybe, I mean, take the factorization example, right? If I give you a prime number, then I don't have any interesting factors of that prime number. So what I want to say is that whenever I give you a composite number, you should give me some interesting factors. So in the language of logic, what this is saying is that for every x, as long as there is a y which makes phi true, the specification true, I should also have phi true with f substituted for y, right? And for every x, this should be an equivalence. I mean, the implication from this side to this side is trivial, because if, of course, I have some fx which makes phi true, then certainly I have some y which makes phi true, same fx. So the implication from this side to this side is the more interesting one and the harder one, that whenever I have some y, I should also ensure that whatever f gives me is one such y. There may be other y's also, but at least one such y. Okay. And such functions are, I mean, this is not new. This has been studied in the literature for actually over a century now. So these are what are called Skolem functions. And in the study of first order logic, when we talk about Skolemization, Skolem normal form, basically we are talking about these functions. So, and of course, I could talk about this problem where I say that phi is some formula in some maybe first order logic or even some more richer logic. And the synthesis problem still has the same statement, that you give me the specification in some logic and I want to generate a system that satisfies that. But to keep things simple, what we will do is in the rest of the talk, I will just assume that all the variables are Boolean, all the formulas are Boolean, and we will see that this problem itself is quite hard. Okay. If we generalize a little bit from Boolean, I will talk about it absolutely towards the end. I mean, we have some work on that also, but this problem soon becomes uncomputable, undecidable, if we generalize before Boolean a little bit more. At least for Booleans, we know how to solve it, but it already becomes very hard to solve. Okay. So here's an example just to make sure all of us are on the same page. So I want to design a system which has two inputs, x1 and x2, has one output y1, right? Like the box that I showed earlier. And this is the relation I want between x1, x2 and y1, that this formula should be satisfied. x1 or x2 or y1 should be satisfied. Okay. So one possible way of designing y1 as a function of x1 and x2 could be to just say, okay, let's just take negation of x1 and x1 or x2, because clearly if I plug that in, x1 or x2 or negation x1 or x2 will certainly always be true, right? So starting from this specification, I came up with this specific function, specific implementation, which satisfies this formula, and we can come up with a proof that this formula is always true. And of course, if you draw out the truth table, you see that this function is already, whenever this exists, phi of xy is true, phi of x fx is also true. Okay? Not very hard in this example. So we have basically satisfied what this relation that we said. For every x, whenever there is a y, then f should also serve that purpose. Now, interestingly, in this example, I give you one function which satisfies this property. But if you just think about it for a few more minutes, you'll see that there are many other such functions which I can also use for y, which will all satisfy this property. Right? For example, I could just use negation x1 over here. That would also work. I could use negation y1, that would work. And in an extreme case, I could just set y1 to true always, and that will also work. Right? So this slide shows that given a specification, there may not be a unique way of implementing the system. There may be many ways of implementing the system. And of course, this looks a little bit more complicated than this, and this looks a little bit more complicated than this. So one can ask that given a specification, give me the simplest under certain criteria system that implements it with a proof that it is actually implementing that, right? So this brings in more dimensions to the problem, that I could talk about automated synthesis, which not only satisfies the specification, but is also optimal with respect to some criteria. Okay, that becomes once again an even more harder problem. Okay, so here is the factorization example I was talking about. So let us say I'm trying to design a system which takes an n-bit number and gives out two n-bit numbers. Okay, and let's say I've fixed n. Let us say n is 256. So it will take a 256-bit unsigned integer and it will spit out two 256-bit unsigned integers. And what is the relation that I want between the inputs and the outputs? I want x to be the product of y1 and y2. I can write this down in terms of the individual bits, not very hard. For n-bit integers, this is roughly order n squared size. Multiplication I can write down in roughly order n squared size. And to make things interesting, I should say that I don't want the trivial factors over here. You should not give me y1 is 1 and y2 is x. So I'm preventing you from setting any of the y's to 1. So neither y1 nor y2 should be 1. And this is now my specification. It is giving me a desired relation between inputs and outputs. And if we look at it, we know that we're asking for non-trivial factors. Okay? Now, it's not very hard to write this. In fact, even if you expand it out in terms of all the n bits, there's a formula of size roughly n squared. It's not very large. But I'm really asking for non-trivial factors of x. And I mean, if we could solve this problem efficiently, we would break RSA crypto system, which is relying on factorization, hardness of factorization. So efficient solution would break crypto systems. So this is just to show that this problem is not going to be very easy, even if I just restrict myself to Boolean variables, Boolean functions, because there are some things on which billions of dollars are resting on the assurance that factorization is hard. And this is really a specific instance of the synthesis problem. And there's another nice thing that this example shows, that it's asking that, well, I give you this specification and my requirement was that for every x I give you, you should give me y1 and y2 which satisfies this. But is it even possible to do this for every x? For example, what happens if x is a prime number? Then the only way of factorizing it is to have 1 and the same number itself. So clearly there are some x's for which there are no y1s and y2s which will satisfy this, right? And this can happen in real life specifications. So what we are saying is that therefore we are not going to insist that for every x this is going to happen, but for whichever x there exists y1 and y2, we must find the right ones, right? So if you go back here, right? So this is an implication. For every x, if there exists some y, then this should be satisfied. It's not that for every x, it's not that I'm just saying that for every x this formula should be true. Right? And this is once again driven by very practical considerations. And even for such examples, I mean, the synthesis problem is still very meaningful, still very useful. And we want to say that, well, if you've already given me an x for which no y is going to work, then I don't care what y you give me, because nothing is going to work. But for all the other cases where there are some y's, I want you to give me some right y. Okay. Okay, good. So if all of us are on the same page here, let me just tell you a little bit about the story of this Skolem functions. Very colorful story. This business started off, as I said, almost 100 years back. Thuraf Skolem was trying to see if actually he was trying to prove a very famous theorem in first order logic called the Lowenheim-Skolem theorem, and he was trying to come up with a better proof. This proof had already existed, and he was trying to come up with a shorter and better proof. And he came up with this insight that in first order logic, we can trade off quantifiers for function symbols. You can get rid of quantifiers if you're willing to introduce new function symbols. And these function symbols are called Skolem functions. So the formula where you remove all existential quantifiers and put in function symbols are called the Skolem normal form. And there's a very rich, and of course, almost around the same time, there was also work by Jaak Herbrand, who was also trying to look at the same problem, but from a different perspective. And their very seminal work, it focused on the existence of these functions, not about how to synthesize these functions. And what does the existence of these functions mean how they can simplify reasoning and logic and all of that. Interestingly, we found out that we can trace this problem even further back all the way up to George Boole. In 1847, he was actually trying to look at some problem which is called the Boolean unification problem. And there is a close connection of Boolean unification with Skolem functions, which of course George Boole did not know at that time. This came almost 50 years later. But this synthesis problem is a very old problem. We are not inventing this problem, right? People have talked about it in different contexts using different names, but pretty much it's the same problem. Okay? And even Lowenheim looked at it in early 20th century. Okay. Now, so a problem that so many people have looked at for so many years must be interesting, must also have connections to several other things. So, and indeed it is. So here I've tried to sort of list down some of the applications of this. For example, it is used in program synthesis. Of course, that's where we started off with. It is used in solving quantified Boolean formulas, finding out whether a quantified Boolean formula is true or false. Is used in planning. It's used to eliminate quantifiers. Of course, that comes from the definition. It's used in circuit repair. It is used in reactive synthesis, where you want to synthesize sequential controllers satisfying specific properties. And actually, this is an incomplete picture. There are many, many other applications of this. And not surprisingly, several people have looked at this problem. I mean, we are not the first ones to look at it. And several techniques have been published in the literature for looking at this problem. And what I'm going to talk about today are two things, two of these approaches. One is this knowledge compilation and guess check repair, which we have pursued very aggressively in our group and which I think are currently the most scalable among all the other techniques. At least that's what our experiments show. Okay. So, so here is my promised cellular automata slide. I was actually able to find out some connection of this, but of course, I'm no expert on cellular automata, so feel free to shoot me down over here. So I was looking at this Conway's game of life, which I'm sure all of you are familiar with. It's a 2D grid of cells. Each cell is alive or dead in a generation, and then there are some rules, right? Some rules which make from one generation to the next, from one step to the next, whether a cell lives or whether a cell dies, there are some rules. And there's this problem here, and that's a snapshot of something. There is a problem here which is called the Garden of Eden problem, which I'm sure probably all of you are also familiar with, which is that is there configuration of this grid of cells that has no predecessor? That is, I mean, you can't come from one configuration to that configuration. There's some very interesting Garden of Eden theorem that I was looking at. I'm sure all of you are familiar with this, which tells you when does a cellular automata have a Garden of Eden or not have a Garden of Eden. And one thing that I was thinking is that so given a cellular automata, basically you give the rules by which you go from one configuration to another configuration. If there is no Garden of Eden, then I should be able to give a witnessing function that defines the predecessor of any configuration. Because if indeed there is no Garden of Eden, every configuration has a predecessor. And one can pose this problem, and actually, as I said, from 1971 onwards, there has been a lot of interest in this game of life and even Garden of Eden. And currently, I was looking at the Wikipedia page for this. There are several Gardens of Eden that are known, but apparently it is some problems about Garden of Eden are still open, and we do not know whether there exists Garden of Eden with whatever, some height less than 4 or something, this, that. And one way that I could formulate this as a Skolem function synthesis problem is as follows, and I'll tell you why this may be interesting. Once again, I'm no expert on cellular automata. So I could certainly write this, and these rules are usually quite simple in cellular automata. They are not very complicated rules. So I could indeed write a specification which has, let us say, inputs X and output Y, where X denotes the current configuration and Y denotes the previous configuration. And this relation tells me what is the relation between previous and next configuration. And the Garden of Eden question is really this. We are asking for all current configurations, does there exist a previous configuration such that this relation is satisfied, right? And if you think about it, this is exactly in the form that we talked about a bit earlier. For all inputs, does there exist an output such that some relation is satisfied? And I could now ask that, well, instead of just telling me this, a yes no answer, saying whether a Garden of Eden exists or doesn't exist, right? A yes answer to this would mean that there is no Garden of Eden. A no answer to this would mean that there is a Garden of Eden. I could also say that, can you give me y as a function of x? Which means if I give you the current configuration, can you tell me from what previous configuration I could come, right? And then one might, so that way it is, a witness that Garden of Eden does not exist is indeed a Skolem function for y. And that way, one can say that, well, okay, maybe all the interesting cellular automata that you care about, you already know whether there's a Garden of Eden or not. So why would this even be useful? But then if you think about it a little bit more, I mean, this is going to come as a formula here. So, and this is kind of specifying the relation between the inputs and the outputs. I could actually put more inputs here, which are defining the rules of the cellular automata. So I could have a formula where, so there are, I think, different ways of specifying rules for cellular automata. And I could use inputs which are specifying the rules and the current input, and I want to know if there is a predecessor. And that would be very interesting, because then a Skolem function would take a rule and an input, and it would tell me what the predecessor for that input would be under that rule. So if I can find out Skolem functions in this formulation of the problem, that would be in some sense a one-shot way of solving the Garden of Eden problem for all kinds of cellular automata whose rules you can specify in a logical formalism. Okay, so I've not tried this problem myself. I don't know how difficult it's going to get, but it looks like there is some connection with Skolem functions also over here. If you're not just interested in a yes/no question, but if you also want to know, how do you get the predecessor, and also if you want to know how do you want to get the predecessor for a cellular automata that you don't want to fix a priori. I mean, you want to have programmability in the cellular automata, and still for that you want to derive this predecessor. So that will be my pitch for using synthesis for the cellular automata research community. I really do not know much about this. Maybe this problem doesn't make sense. Please come and feel free to tell me on my face there's a solved problem or something. But this is what I thought, at least to this audience, hopefully this is interesting. Okay, so now that we understand what Boolean functional synthesis is, we have seen some applications. It's interesting to ask, how hard is this problem? And what we're going to do is, I mean, whenever we want to talk about hardness of problems, we have to decide how are we representing these formulas, how are we representing these functions. So we are going to represent them in a very general way as Boolean circuits, negation normal form Boolean circuits. So I'm not putting any restrictions on how I mean, any way that you can represent them, which can be represented as a circuit, we are doing okay. And then we have some, immediate results that this is NP hard. Certainly, it cannot be. I mean, I can solve the satisfiability problem with this very easily. But a little bit more interestingly, it turns out. So what NP hard just means is that you'll require a lot of time to solve this problem in general, right? But suppose I told you I have all the time in the world. I'm willing to spend all of that time. But can you give me a nice, remember I showed you some Skolem functions that are very small, simple, and others were more complicated. So if I tell you that I'll give you all the time in the world, but can you give me very small and simple Skolem functions? So it turns out that we can't do that in general, because there is a space complexity result that we have in this area. And without going into the details of this, let me just say that uh, unless some very long-standing complexity theoretic conjectures are falsified, something like P equal to NP, unless this is falsified, right? So this is not about P is NP, but this is at the next level of the hierarchy, saying second level of the polynomial hierarchy, if everything collapses. I mean, this is widely believed not to be true, but still an open question in complexity theory. So unless some such drastic thing happens in complexity theory, uh, we will always have specifications for which the Skolem functions are going to be very, very large. The smallest Skolem function is going to be very large. Okay. So this just means that even if you spent all the time that you had, you're not going to get very small Skolem functions just because of the inherent hardness of the problem. Okay. And this looks like very bleak news. I mean, time-wise, we are doing bad. Space-wise, we are doing bad. So are we really in business or not? Here is where I think our work comes in. So there is a little silver lining over there. And the first one, which I'm going to spend a few slides on, and the second one, I'm going to spend a few more slides on. So in the first one, we said that, well, yeah, we can talk about an algorithmic paradigm. And for lack of a better word, I call it guess, check, repair. But we will see that this is not just arbitrary guess. This is guessing in a very systematic way. And this we have found it to work very well in practice. In fact, this is the best thing that we know in terms of how far it can scale. Okay. But then we have also been looking at this other thing, saying that, well, if the formula phi, we said that we can represent it as some arbitrary Boolean circuit. Now, if we are willing to impose a little bit of structure on this circuit, it turns out that we can suddenly do synthesis provably efficiently, provably in polynomial time. And so it's interesting to understand what are these structures? Do these structures appear commonly? Is it easy to convert a given circuit to that structure, and so on, right? So these are the two things that I'm going to talk about. And in this bleak landscape from a complexity theoretic point of view, I think these have shown us that, yes, there indeed is some hope in practice. Okay, so here's the guess, check, repair paradigm. There is a long recent line of work, several of it from our group, several of it from other groups. And the basic idea here is the following, that you start with the input specification. Remember, we always start with the specification, and our goal is to come up with the function that I can replace for y. Yes, you have a question? Oh, that we can replace for y. And so what we do is we take the specification, do some pre-processing. I mean, this has been a huge learning experience for me, that how important pre-processing is. I mean, it really makes the difference between being able to solve a problem and not being able to solve the problem. So we do some pre-processing. These are very simple algorithmically, but they're extremely effective in practice. And then we do what is called like a guessing step, but I'm going to talk more about this guessing step. It's not just some blind guess. And then we go and check. After we have guessed, we go and check if whatever we have guessed really meets the property of a Skolem function. And if the answer is yes, we are done. If the answer is no, then we try to repair the checked, the guessed function, and then we check it again. And we do this in a way where there is a guarantee that this loop will eventually terminate. It's not that it's going to go into an indefinite loop. And so finally, we're going to come out of this, right? So this is at a very high level what the guess, check, repair paradigm is. And in some sense, this is how, when we try to approach hard problems, a lot of us try to do it this way. We try to guess that, okay, maybe this will work. Then we try to check whether it really works. And then we go and try to fix what did not work. And this was really motivated by that. Okay. So this pre-processing, as I said, these are most often very simple, very efficiently implementable, but they're extremely effective. The check part, this is where, as I said, that we need some guarantees that whatever the guessed functions are really satisfying the specification. If not, how are we repairing it? And why does this repair always terminate, in the sense that we don't keep moving around this forever? So here we use techniques from logic, which give us very strong guarantees. And for the guessing, there are at least two dominant ways to do this. One is data-driven, where this is not done by our group, done by some other group, where they have even brought in machine learning to do this guessing. I mean, I don't understand much about that. I'll show you some one slide of how that is done. So our approach has really been about doing function approximations. But in the interest of time, I think this is more easily explainable. Function approximation requires more technical explanation. So I will just quickly show what is done over here. I'll explain what is done in check and repair so that you get an idea of how this whole thing fits in. Maybe for cellular automata, there are other ways to guess right things. Maybe there are domain specific ways. Okay, so this is the data driven guessing. So what is done is that you're given the specification, and so what you do is you go and try to find out some samples of inputs and outputs that satisfy the specification. Remember, we talked about specification by examples. This is really saying from the formula, let's come up with some samples, and then you feed these samples to existing machine learning techniques, and this is decision tree learning techniques, and they sort of give you some idea of what these functions could be at a very high level, right? Of course, there are more details over here, so let's not get into that in the interest of time. But I think this is kind of saying that let's gather some data and then let's try to learn some pattern from the data. We are just guessing. There are no guarantees that the guessed functions are correct, but the check repair step will enforce that if there was something wrong. So the check repair step is the more interesting step. Okay, so how do we check, right? So at this point, we have guessed some functions, but we want to know whether this formula holds, because that was our final litmus test, that this should hold, right? So if you stare at it for a minute, this looks like we have to check whether some quantified Boolean formula is true or not. And yes, we could use QBF solvers for doing this, but turns out that QBF solvers are not really as mature, as scalable as if we could give it a formula without the quantifiers, satisfiability solvers. So we asked the question that can we avoid QBF reasoning and use just satisfiability based reasoning? So no quantifier alternation. We don't want this two kinds of quantifiers in there. Can we do this? And it turns out that yes, we can. And I've just shown you a little formula here. I'll just walk you through it. It's not very hard. So remember, our specification was in terms of x and y, and I'm going to write out a formula which has x, y, and a second copy of the y's, which I'll call y prime. And this has a copy of the specification. It has a copy of the specification negated using the second copy of y's, and it says that the second copy of y's are always equal to whatever my guessed function was, right? So if you look at this formula, why do I have these three parts? So suppose I have a satisfying assignment of this formula, right? Values of x, y, and y prime that satisfy this formula. What does it mean? It means that the x and y satisfy phi, which means that for x, indeed there was a y that satisfied the specification. But the x and y prime don't satisfy the phi, which means for that same x, the y prime does not satisfy the specification. And that y prime was exactly equal to what fx was giving, right? So it's basically saying that now I have an x for which I know that there is a y that satisfies the specification, but the fx that you gave me is not going to satisfy the specification, right? So every satisfying assignment tells me that f is not correct. There's some mistake in f, right? Because I found an x for which I could find a y that satisfies the specification, but f of x gives me something which violates the specification. So I need to do a repair, right? So every satisfying assignment, I just explained this, is a counterexample to the claim that I have got the correct Skolem functions. And if this formula becomes unsatisfiable, which means that there are no counterexamples to this claim, it means that you have obtained the right Skolem functions. So here I have one formula and there are no quantifier alternations, and I'm just trying to check whether it is satisfiable or not. If I figure out that it is satisfiable, I know that I have a problem and I have to go and fix. If I find out that this is not satisfiable, I know that my functions are correct, and I can output those as my Skolem functions, right? And here there is no quantifier alternation here. So we've gotten rid of this. So how do we do the repair? So let us look at the same formula again, which we call the error formula. Every satisfying assignment of this tells us that there is some error. And let us say that this was a counter example. So it gives me some values of x. It gives me some values of y for which the specification is satisfied. And it also gives me some values of y which are returned, which are computed by the Skolem function, but that don't satisfy the specification. And here the coloring I have done is to say that the right value of y seems to differ, right value of y1 seems to differ from the value of y1 prime, and the right value of y2 also seems to differ from. So it looks like both y1 and y2 were wrong over here, right? But then if you think about it for a little bit, this is just one satisfying assignment. There could be other satisfying assignments. And so, we would say that, well, all the places where these y's are differing, we need to go and repair f. But then we can be a little bit smarter and we can say that, well, could there have been another satisfying assignment of the same formula where maybe the mismatches are fewer? And maybe this is another satisfying assignment of the same formula where these two are matching, but these two are still differing, right? Because the same formula can have multiple satisfying assignments. So what this is saying is that for this given x, right, x1 is 1, x2 is 1, probably there was no problem with y1, but there was a problem with y2, right? Because there are different ways to satisfy this formula. And by setting y1 is 0 and y2 is 1, I can satisfy this formula phi. By setting y1 is 1 and y2 is 1, I can also satisfy the formula phi. Here I looked at just one way, here is another way, but since in this way it matches what my Skolem function is giving, so maybe this is a better form, this is a better satisfying assignment to work with, because I can just fix the y2. I don't need to fix the y1 over here, right? So this can be formulated in a more rigorous way using what is called maximum satisfiability. So I'll not get into that. Basically, we are saying we can pose this as an optimization problem where we try to have matches between y and y prime as far as possible, and only things that don't match, we're going to fix those. How do we fix? So it's kind of simple. In fixing, we say that, well, every time I have such a counterexample, I know that there is a certain input for which this output has become wrong. So I will say that, okay, whenever x1 is true and x2 is true and y1 is false, make sure that y2 is set to true, which is the right thing, and y2 is not false, right? So I started off with my original function, which was guessed, and then I used this technique of using the error formula to find some counterexamples where that function didn't work, and then I used that counterexample to modify the function to make sure that it matches with the right output wherever possible. And if you think about it, every time I do this repair, I have taken care of one input combination. And because there are only finitely many input combinations, it will finally terminate and we will get the right scoring function. Okay, so that's about the guess check repair approach. The other approach, okay, should have been a recent, not recent. The other approach, which is trying to write down the specification in a form that allows you to do efficient synthesis, is called knowledge compilation. And here the question we are asking is that, can we compile the specification to a form such that after it synthesis is very efficient, right? So, and in particular, remember at the beginning I talked about there can be many Skolem functions for the same specification. So I would like to compile it to a form from which it is easy to synthesize all of them, and more interestingly, it's easy to explore that design space and maybe find out the best one. And this is the knowledge compilation approach, where we take the input formula, again do some pre-processing, then we pass it through a compiler. What this compiler is doing is it's taking this formula over here and it's spitting it out in a different form, and such that after you get it down to this form, we are guaranteed that there are efficient synthesis algorithms. In polynomial time, we can do the synthesis, right? So of course, this compiler is going to be the big bottleneck over here, because we know that the problem is hard in general. And if we can get it down to the right form, then synthesis becomes easy. So there are no free lunches, so the compiler is going to be hard. And indeed, in general, this compilation is not easy. Okay. So the question is, how do we define such a normal form? And we came up with something called the Skolem basis, which allows us to get this normal form. And how do we compile to this form? And here, once again, we came up with what is called a counterexample guided way, which is an incremental compilation approach, which allows us to do this efficiently. Okay, so let's see. I have maybe close to 5 minutes or 8 minutes. Let's see how far we can go. So how do we come up with this form? What is this compiled form from which we can get all the Scholam functions easily? So to answer this question, we looked at the theory of Boolean functions and how do we represent sets of Boolean functions, because I could have many Scholam functions for a given specification. And I mean, this is something that we came up with, but of course motivated by what's there in the literature. So we say a set of Boolean functions. In our case, these would be the Scholam functions. It has a basis, means it can be compactly represented by two such functions, ax and bx. So this is the space of all assignments of x, and there is a set of Boolean functions over here, and I want to represent them compactly. So we can do that using two functions, ax and bx. If I mean, we say that this basis exists if ax and bx are mutually orthogonal, so to say, so that there's no common satisfying assignment. And for every function in this set f, I can get it by augmenting a but not going outside b. Right? So it's between a and a or b. So pictorially, if you think of this a as the inner circle, all the assignments within that represent a, and b as this annular region. I think I had this somewhere here, the annular region which doesn't intersect with a but stays outside a. Then all these functions in this class are basically things in between, where of course this white gap is just there to denote that they are disjoint, right? So it has to include all of a, and it cannot go outside a or b. And this gives one way of defining a large class of Boolean functions. Not every set of Boolean functions can be represented like this. Not every set of functions has a basis. But it turns out that we were able to show that no matter what specification you give me, the set of all Scholam functions for it always has a basis like this. So the set of all Scholam functions for an output in a specification always has a basis, and not only that, it actually has a unique basis if you fix some ordering on the outputs. So this was interesting because it said that, well, we can represent all the Scholam functions, the entire space of Scholam functions, in a nice and compact way. And it turns out that this is kind of the representation. So if I have this a and b for my specification phi and for the output y, every Scholam function is something like this, where this h is an arbitrary Boolean function. And you can see that this includes the whole of a, it never goes outside a or b. And by just varying h, you can put whatever Boolean function you have for h. You will get something between a or b. And from the Scholam basis result, we know that that's a Scholam function. So this gives us a way of parametrically calculating the set of all Scholam functions from a given specification. Okay. And for those of you who are familiar with logic synthesis, this is like saying A is the onset and B is the don't care set, and you can go and synthesize any function which includes the onset, includes any subset of the don't care set, and you have a Scholam function. So this is actually interesting because it allows us to use logic synthesis tools to optimize Scholam functions once we have the Scholam basis for it. Okay. And then, of course, by using specific values of h here, we can show that there are some very simple Scholam functions. For every specification phi with a single output, if I just set that output to 1, I already get a Scholam function. If I set the output to 0 and negate the resulting function, I already get a Scholam function. So all of these follow from this. Okay. So in the interest of time, I will just say that if the specification has a single output, there are closed form formulas we can come up with to get this Scholam basis A and B. If the specification has multiple outputs, we need to do some simplification. So we need to get this Scholam function one output at a time. And as we are going from one output to the next output, we need to do some processing of the specification. In particular, we need to quantify out all of those variables for which we have already obtained the Scholam basis. And then that allows us to get the Scholam basis for the next variable. and then we quantify that out, and that allows us to get the Skolem basis for the next variable, and so on. So, if you look at this slide, it looks like calculating Skolem basis is easy for a single output specification. For multiple output specification, also it is easy if you could do this quantification efficiently. So the question is, can we do this quantification efficiently, where phi is given to us as a circuit, and so we are given phi as a circuit, and we want to obtain exists y phi also as a circuit, and we want to do this efficiently. And so here is a simple example. So let us say this is a circuit with AND OR gates, negation normal form, so all the negations appear at the leaves, x1 and x2 are the inputs, y is the output. So this is some specification, right? And I want to do exists y, I want to get exists y phi as a circuit. So the simplest way to do this is to make two copies of it, set y to 1 in one of them, set y to 0 in the other, and just OR them up. Right? That's by definition exists y phi xy. The only problem with this is that it doubles up the size of the circuit, right? And so if I have to now do this quantification over n variables, it will become 2 raised to n size. So the question is, can we avoid this doubling and still be able to do the quantification? Because once we can do that, we can get the Skolem basis efficiently, and then we can do Skolem synthesis efficiently. And so once again, looking at this example, it turns out that this one where I set y to 1 simplifies to x1, and this one where I set y to 0 simplifies to x1 or x2. So if I try to take the OR of these two, this already implies this, so the OR of these two is going to be just this, right? So it looks like there are some cases where we can get away with getting the exists y phi without doubling. But of course, these are very special cases. And I mean, these kinds of things where setting y to 1 implies setting y to 0, so called negative unate. We can also have positive unate over here. But then, we may not get so lucky, and the specification may not have such property. So what do we do when the specification does not have such nice property? Can we still avoid the doubling and get the existential quantification? So here, so in the interest of time, what I'll do is I'll just quickly skip through some of the slides. And what we did is we were able to identify the root cause of why this blow up happens during quantification. And the root cause is something like this, that there is an AND gate, specifically AND gate inside the circuit, and there is a path from it to Y, and there is another path from it to negation Y. And if we have such AND gates, then that's problematic. This is what we call a conflict, and this hinders efficient quantification, and this is the root cause of the problem. If I can build this circuit without this property, then quantification is extremely easy. So what we did is we said, okay, how do we catch whether there are such AND gates, because the circuit can be large? So we did a little trick. We renamed the negation Y to a new variable, Y hat. And we said, okay, so now at the root, I have a function on whatever the X is and Y hats. And I ask, can I make this equivalent to Y and Y hat? Unless there is an AND gate which has paths from both Y and Y hat, which can be actually exercised, we cannot make it equivalent to Y and Y hat. And so this is the question that we ask. And if so, then we say there is a conflict, and the assignment to the other variables that makes it equivalent to this is called the counterexample, the conflict freeness. And if it is no, then we have conflict free, and then we can do efficient quantification just by setting these to true. We can just take the circuit, and if it is already conflict free, we can just set these to true. So it's actually in a constant time we can get a circuit which gives us exists y phi xy. So we developed this idea a little bit more, and let me skip over these slides. This was just trying to show how we do the counterexample driven incremental compilation. And all I want to say is that once again, we realize that people have looked at such things in the past, particularly in the artificial intelligence community. People have looked at ways of representing functions which has some nice properties. And so there is this thing called decomposable negation normal form, which is exactly good for synthesis as well. We were able to weaken it a little bit, getting weak decomposable negation normal form. we were able to weaken it further, getting what we call synthesis negation normal form. This is similar to what I just told you. We rename the variables and then look at it. And this also turns out is sufficient for polynomial time synthesis. And yeah, let me skip this in the interests of time. And then we went ahead and asked the question that, this new synthesis negation normal form, how does it relate to other things that are already there in the literature? For example, some of you may be familiar with this binary decision diagrams, which are also one ways of representing Boolean functions. So how does this relate to binary decision diagrams? And we were able to show several relations that these are more succinct than all of these things that were previously known. And then we said that, well, we got a sufficient condition. This synthesis negation normal form was a sufficient condition for efficient synthesis. Do we also have a necessary condition for efficient synthesis? And basically we were asking, is there a normal form for which I can do efficient synthesis? And if there is any other class from which I can do efficient synthesis, I can compile that class to this normal form efficiently in polynomial time and also in polynomial size. And this sounded quite ambitious, saying that, is there one, the best class to which everything should be compiled if we want to do efficient synthesis? But fortunately, we were able to show that this exists. There exists such a class, which is kind of sitting above all of these. And any class of circuits from which synthesis is efficiently doable can be compiled to this class efficiently. And this is called the subset unrealizable normal form. Let me not get into the technicalities of it. It's a generalization of SYN and NF. And we can again look at how this most general form relates to others. So this is strictly more succinct than others. So so with that, maybe I'll come to the summary slide, saying that hopefully I have been able to convince you. The takeaway message is that there is some problem called functional synthesis, which has been looked at for a very long time. Still, we don't have very good solutions. And it has diverse applications. And I'll be really happy to talk to some of you if there are some applications within the cellular automata domain. And despite the inherent complexity, theoretic hardness of the problem, I think over the last 10 years, at least our group and other groups, we have been able to push the scalability envelope. So currently we are actually able to synthesize Skolem functions for specifications with a few thousand outputs, a few thousand inputs. The circuit is a few 100,000 gates. And we are able to automatically synthesize the Skolem function for it. For the factorization problem, it's a really hard problem. So we are able to automatically synthesize factorization circuits, where I think we have been able to go to factorizing 24-bit numbers, which is still very far away from breaking RSA, which is using 128-bit or 256-bit numbers. And over the years, this thing has been improving. So we started off with some 600 odd benchmarks from the community. And I think, a few years back, this is not from our group, this is from some other group. They were able to solve more than 500 of them. Today it is slightly more, we are close to 550, but there are still challenging problems to solve. And hopefully I've been able to sort of convey this, that this is a problem which has nice theory behind it, but just theory is not good enough if we want to get it to practice. So we also have to come up with efficient algorithms that work well in practice. And we still don't know why a large class of problems can be easily solved, although they don't seem to fit any of these nice normal forms, compiled forms, all of this. Where do we go from here? We need more benchmarks. My appeal to the cellular automata community is that if you find this problem interesting, give us your hardest problems, and we'd like to see this advances the technology even for synthesis, and hopefully it's beneficial to you as well. A notion of quality, as I said, that there could be multiple Skolem functions when we want to choose the best one. And we have also started working on beyond propositional logic, first order logic in its generality. We did some work on this. It turns out that almost everything is undecidable over there. So recently we were able to solve the problem for Presburger arithmetic, for polynomial constraints over reals. Once again, we can solve the problem over rationals. We don't know how to solve the problem fully. So going a little bit beyond Boolean already gives major computational hurdles. But with that, I have overshot my time by 5 minutes, but I think I also started 5 minutes later. So I'm just around 60 minutes. So thank you, and I'm happy to take questions. Yes.
Sir, my question is might be too basic that you have that in the diagram that pre-processing and then guess and then check. I would like to know the what is the upper bound of the time complexity of checking of the algorithm. In the first few slides, there was a
The check, where we have the check? Yeah.
check and repair, check and repair.
Yes, yes. Yeah, let me get to that slide.
No, previous one. This is the second method. Yeah,
This one.
this one. I'd like to know that what is the time complexity required to check for any function.
So check is this step over here, right? So our check is saying construct this formula and find a satisfying assignment of the formula. So this formula is completely propositional. There are no quantifiers there.
Oh,
right?
Yeah.
So this is an NP-complete problem.
Okay. And the second,
right. So yeah, just to complete my answer to that question. So this step is NP-complete, and one might say that how did it help, right? But then I also showed you that the problem is NP-hard. So there is no way of escaping this complexity in the worst case, right? From complexity theory, we know the problem is NP-hard. So I cannot escape an NP call, a call to an NP solver, right? But then the interesting part for us was that if you have worked with satisfiability solvers, have you ever used a satisfiability solver proposition? So yeah, we can talk more about it. I mean, satisfiability solvers today on my laptop, I have satisfiability solver. I can solve a problem with close to 1 million variables in half an hour on my laptop. So the technology for satisfiability solving has advanced so much that earlier we used to think if some problem is NP complete, it's bad. It's too hard a problem. Now we almost think that it's a solved problem because just throw it to a SAT solver. In fact, if you go to the Wikipedia page for the Garden of Eden, some of the Gardens of Eden have been found using satisfiability solvers, the latest satisfiability solvers. So these are really very, very powerful engines. And so our goal was to get it down to a form where we can throw it. Yes, complexity theoretically, this is still, we have not escaped because we cannot escape. There is a lower bound over there, NP hardness. But once we get it down to this form, which is different from this form, I mean, QBF solvers are still a long distance away from satisfiability solvers. They don't scale as much as satisfiability solvers. So our goal was to avoid this, get it down to a problem that we can throw to a satisfiability solver. And then, we can, in practice, solve this problem reasonably efficiently. So yes, the complexity is NP complete, but in practice, getting this formula really was a big game changer for us, because once we have something we can throw to a SAT solver, as I was saying, we have formulas with a few thousand outputs, few thousand inputs, and these functions are themselves few tens of thousand gates. So it's a fairly large formula. But even on my laptop, in fact, I had planned on showing a demo, but of course, I didn't have the time. I have a demo on my laptop. I can show it to you if you're interested.
definitely, I will like to see this.
So getting this down here was a crucial step that we can now throw it to a satisfiability solver. You had another question.
Yes, sir. My another question is I have some problems in my mind currently based on the CA. I will discuss it later if I may chance. So my problem is there any particular problem that cannot be solved strictly, you can say that it cannot be solved by this scheme or by this methods. Is there any, I mean, hardest problem?
I mean, so for Booleans, we know it is always solvable. It's just how much time it takes, how
Yeah.
much space it takes. But as I was saying in the last slide, if I go to first order, oops, I think I ended up doing something. So if you go to first order logic, yeah, there are unsolvable problems there. We can show that the synthesis problem is undecidable, which means that there is no algorithm. So there are classes of first order logic formulas, specifications. So there are classes of specifications in first order logic for which it is impossible to come up with an algorithm which will generate the right Skolem function for all first order logic specifications in that class. So yes, there are unsolvable problems. I mean, and we are very close to that. I mean, Boolean is already hard. If we go a little bit more, it becomes, but then there are some fragments of first order logic like Pressburger arithmetic. Pressburger is basically integers with addition, no multiplication. So you can have unboundedly large integers with, so you can't represent it using propositional logic because you're talking about infinitely many values. Uh, Pressburger arithmetic is decidable, and we actually have very recent work. We have been able to come up with a synthesis algorithm for Pressburger. Similarly, reals, and where the constraints are polynomials, so you can say, you know, suppose I say that x squared plus y squared is greater than 1 and less than 4. I'm describing an annular circular region. And I say x is the input and y is the output. I want to come up with a function which, given an x, will give me a y such that all of this is satisfied. This can be solved. Okay. Real numbers, polynomial constraints, we can solve it. Rational numbers, polynomial constraints, we cannot. So it is an open problem actually. Yeah, we don't know whether it can be solved.
Thank
So
you.
yeah, I mean, there are very fine boundaries we cross, it suddenly becomes undecidable. Few things that are decidable. Yeah.
Thank you. Thank you, sir.
Yes. Yes. Yes.
Professor Supratik, I'm really enlightened. But long back, I was thinking about, there was one issue of and logic, and you used that. And
This
I
one.
was trying to, long back, this is not my area.
Okay. Okay.
Long back, I was trying to, how to get nearer to a linear function, linear Boolean functions from the non-linear domain.
Mhm.
So, and or putting severe problems.
Right.
So I want from you, around your knowledge, how to get closer, non-linear functions closer to the linear domain and farthest from the linear domain. Can you give me some idea?
Yeah, I'm not sure if I fully
Non-linear
understood.
domain is very far.
So if I put ands and ors, it is non-linear, clearly. So linear would be XORs, is it? Yeah. So, but XOR is not a universal gate, right? So I can't synthesize every Boolean function using XORs. If your question is that if my specification has only XORs, does it make things simpler? If that is your question, I think if it has only XORs, I can use Gaussian elimination. And I can synthesize the functions also as XORs. Okay, if it is only XORs, but if you add XORs with negation, I think once again we are in trouble.
No, what exactly I was asking, that is a linear domain and non-linear domain is quite high. Can you specify non-linear Boolean functions which are much nearer to the linear domain and another farthest from the linear domain?
Okay.
Are you getting me?
So you want some class of functions which are close to the linear domain and far away. So what is the metric of closeness that you are using? I mean, when do I say that something is closer than something else? So in order to talk about closest or farthest, I have to be able to compare the distances. So I do not know. Maybe there are metrics that are used there. Yeah, so we need to have some distance metric between two functions in order to, I mean, clearly there are linear and non-linear, but if one nonlinear function is farther than another nonlinear function from the space of linear functions, I do not know what the right metric to use there, what the right distance metric to use there. So it will have to depend on a distance metric, right? So
I think
yeah, maybe we can discuss it offline as well. Yeah, I think Supriti had a question. Oh yes, yeah. Please.
A short question. Can you relate your problems to because in practice you may be satisfied or may accept functions or algorithms which are output of genetic algorithm, genetic programming.
Mm-hmm.
So in the practice, I mean, you may be satisfied
So,
with the solutions that are not complemented some old study, but you in practice you need it.
so that's a very interesting question, and in fact, let me go back. So, in fact, one could go beyond genetic programming and ask, let's just ask ChatGPT. It will give me some result, right? Large language models. And yes, we have tried to look at that angle, but I'll tell you the problem there. Okay, it's a very serious problem which I don't think gets addressed by either genetic algorithms or LLMs. So if you go back to the original problem statement that I gave, right? Yeah. So this is the problem. I also want a proof that what I've synthesized is correct. Otherwise, what use was it, right? So I've given you a specification, maybe something like this, and you're giving me a system, and maybe that system actually works well most of the times, but I need a proof that it works exactly as per the specification all the time. Okay, and this is something where large language models, heuristic techniques, genetic algorithms, this is the part. I mean, sometimes sometimes they produce the system without producing the proof, and maybe we can construct the proof. But sometimes they produce a system. I mean, this, at least we have tried this out with large language models. I mean, we give the specification to the large language model and it outputs a system, doesn't give us a proof. It gives us some reasoning which is clearly not correct. But then when we try to prove that that system is, whatever it has generated is correct, we realize that it is actually not correct. And there are corner cases where it slips. So I think this is the part where if I insist on a proof of correctness, that's where I think the other approaches failed. Yeah. Yes, Supriti, you had a question.
Sir, it was a very nice, very nice talk, sir. Sir, in cellular automata, sometimes we use multiple rules. Like in Garden of Eden theorem, if we suppose we are using multiple rules, and we're trying to see, suppose that whether there is predecessor or not. So in that case, can we have a kind of formula so that we can at least check for some cellular automata with multiple rules that the Garden of Eden satisfies? Is it possible to do that?
My first guess is yes, but I've not tried it out. So we can discuss more about it because, uh, I was looking at the Garden of Eden problem and I looked at, for example, as I said, on the Wikipedia page, there are solutions, Garden of Edens that have been obtained using SAT solvers. And if it can be done using a SAT solver, somebody has already written out this formula, which is relating present state to next state. So if somebody has already done that job, but maybe those are for specific rules.
Yes.
But if I want to now introduce additional rules, so my first guess is that yes, it should be doable. but I have not done this, and maybe we can talk about
Actually,
it. So that we
there are
can,
not very large amount of work on this kind of.
I see. I see.
So we can
Yeah,
actually
sure.
try for
I mean,
this.
one can even think of a synthesis problem where the input are the rules and the output is the Garden of Eden. So I can now try out different rules and immediately get the Garden of Edens from this column function. I think these are, in principle, they're certainly solvable using this technique. How well they work in practice, I mean, if we can work on this and then come up with some hard benchmarks, this also helps the synthesis community because we get some hard benchmarks to work on, right? Yeah, so we should talk more about this. Yeah.
Okay, thank you, sir.
Okay,
So thank you, Supratik, for a very enlightening talk.
thank you.
I realize that I don't know many things, but that's fine.
I think there is some question he has.
Sir, the talk is nice. Actually, I was in online, so
Okay.
uh, so actually, I have one question. When we use the meta heuristic techniques like genetic algorithms and like such techniques, sometimes we stuck at local minima or local maxima. But in your approach, does this problem can be solved?
I mean, do we get stuck in local minima, local maximas? Yeah, so currently, as I said, that we are talking about synthesizing one system which satisfies the specification. And this, there is nothing we are trying to optimize over here. We're trying to come up, right? But the moment you bring in quality and you say that there are multiple systems which can satisfy, right? I think I had a simple example somewhere here. Yeah, so there are multiple Skolem functions and we want to come up with, and it is precisely for this optimization version of the problem that we designed this Skolem basis, which can represent the space of all Skolem functions in a succinct way, so that we can, yeah, where is it? Yes, so this is the Skolem basis, that the set of all Skolem functions has a unique basis. And once we have that basis, we can then start exploring that space. So then we enter the optimization version. Honestly, we have not explored that. I mean, that's some problem that, yeah, I mean, we have not yet started exploring it. We are just trying to find one Skolem function efficiently. But yes, once you start doing optimization, I think you can get stuck in a local minima, and then you have to find out ways to jump out of the local minima. Right? I mean, the difference is that, in this Skolem function thing, even if you're at the local minima, you're guaranteed that it's a correct Skolem function. Every point in the space you're traversing, it's a guaranteed correct Skolem function. You're trying to optimize some other quality, maybe the size or maybe the delay or the power or something. And there we may get stuck in local minima. But wherever you are guaranteed that it's the correct Skolem function. As opposed to genetic algorithms where you can get stuck in a local minima and it may not be a correct Skolem function. It may be some distance away from a correct Skolem function.
Whoever has any more questions, we'll have to ask Supratik directly.
Yeah, most welcome. Oh,
But where are they? I don't even see them. Yeah. So yeah. Okay. So if any of the online participants want to ask a question, this is the time. Please go ahead. No. Okay. Thanks. Okay.
I mean, if somebody has questions, yeah, I'm around today. Please feel free to email me. And yeah, I mean, I'm hoping that there'll be some overlap with the cellular automata community, and there are some problems that we can work on. Thank you very much.